The integral from 0 to 16 of 1 over square root of x dx is a definite integral, but it's also an improper integral. This function, 1 over square root of x squared, is not continuous on the closed interval 0 to 16. So what we have to do is, over to the right, we have the graph, and the highlighted portion is from 0 to 16. We want to see if this does have a definite area. It may not, but let's give it a shot. Now, since the function is not defined exactly at 0, over here we're going to approach 0 from the right side, which is a one-sided limit that you did back in Cal 1. Let me rewrite 1 over square root of x as x to the negative half. Replacing 0 with the letter a, I'm going to let a approach 0 from the right. Take the antiderivative, add 1 to your power, that's x to the positive half, or square root of x. Dividing by the result, dividing by half, is the same as multiplying by 2. We're going to evaluate that at 16 and a, take the difference, and then apply this limit to the a term. 2 times the square root of 16, that's 4 times 2 or 8, minus 2 square root of a, with the limit as a approaches 0 from the right. The closer you get to 0 from the right and take the square root, you're going to approach 0. Just think of it this way. The smaller the number, the smaller your square root. As you approach 0 from the right, this term eliminates and goes to 0, leaving 8. This is called a convergent improper integral, and it has an area of 8 under the curve between it and the x-axis. In the second example, we have the integral from 2 to 3 of 1 over x minus 2 quantity to the 3/2 power. Like the last example, I'm going to bring this up to the numerator. That's going to make it x minus 2. We negate the exponent. This is not defined at 2 because 2 minus 2 is 0. Square root of 0 is 0. Cubed, still 0, but we're not allowed to have 0 in the denominator. Since 2, over here to the right, 2 is where the vertical asymptote occurs, we're going to approach 2 from the right like we approached 0 from the right in the previous example. So we're going to approach 2 from the right. Replace 2 with the letter a, and we're going to have the limit as a goes to 2 from the right. Let's take our antiderivative. We add 1, that brings it to negative half, x minus 2 quantity to the negative half. Dividing by negative half is the same as multiplying by negative 2. So here's our antiderivative. Substitute in 3 for x. Also, I'm going to return this parenthetical term to the denominator and put it back under a radical. So that is 3 minus 2 under the radical. Well, we know that as 1, square root of 1 is 1. Negative 2 divided by 1 is negative 2. Minus a negative, that's why I've got a plus sign here. And then we apply our limit. 2 over a minus 2 under the radical. 2 over square root of a minus 2. As we let a approach 2 from the right, we get closer and closer to 0. Well, if you have a fixed numerator and your denominator gets increasingly closer to 0, then that makes the fraction really large by the time you get it all said and done. So this back limit actually approaches infinity. Well, infinity minus 2 is still infinity, so this is a divergent case. Our third example, we had the improper integral negative infinity to 0. Now, since our lower limit of the integral is infinite, this is an improper integral as well. We're going to replace negative infinity with an a. So we're going to let the limit as a approaches negative infinity, and we're going to integrate from a to 0, e to the 3x dx. The antiderivative is 1/3 e to the 3x. Evaluated it to 0 and a. That gives us 1/3 e to the 3 times 0, which is 1, minus, and then because we're putting in a, we've got to use the limit as a approaches negative infinity, e to the 3a. Well, with e, the more and more negative your power gets, and you can try this on your calculator, like you could type in a to the negative 5, or excuse me, e to the negative 5, e to the negative 20. The more negative your power becomes, the closer that gets to 0. And that actually becomes insignificant. Don't forget, we have 1/3. This first evaluated to 1, so we have 1/3 times 1, which is 1/3. We have a convergent integral. The last example, I did not put a graph on here, and that's on purpose. You don't have to graph these. If you want to graph them and mark off and shade these integral limits, that's totally appropriate. You just don't have to do it to work these. We're going to integrate from 2 to infinity, x to the negative 3. It's easier to integrate if you go ahead and bring that x cubed up, make the power negative. Because of the infinite upper integral limit, this is an improper integral. I'm going to replace, and usually what I do is if I replace the bottom value, I use a. If I replace the top value, I use b. There's no set rule to it, but you want to develop some consistency. So I'm going to replace infinity with b, but note b is going to approach infinity in our limit. Take the antiderivative, add 1 to the power, that's x to the negative 2, divided by negative 2. Return your x to the negative 2 back to the denominator, and this antiderivative is negative 1 over 2x squared. We're going to substitute in b, then a 2, and take the difference. Subtracting a negative is where I'm getting this plus sign. Subtracting a negative. Subbing in b and letting it go to infinity, b squared is going to be really large, especially when it's going to infinity. We have a fixed numerator, an increasingly large denominator. This fraction goes to 0. Minus negative, again, that's why there's a plus sign, 1 over 2 times 2 squared. That 2 goes in for x. That's 4, 8, 1/8. 0 plus 1/8 is a finite number, so this interval converges.